Okay, there's a few. I have a few basic functions that I'm going to need later in the CUDA library. So this time I'm just going to complete them. Just basic functions here. Nothing really that is really that essential, but they're going to be useful later when we go deeper into how neural networks should be used. Okay, the first one is just to copy from mean squared error here. Oh, first thing I need to change something here. It's not essential, but if the function fails, then we turn something different. We have to check. They're just not essential, but just to be clean, return 0. Okay, just to make sure that everything works the way it's supposed to. Okay, now first function, get sum. Okay, what I'm doing is just the. Oh, by the way, the neural network is still running. This is the inside of the neurons. So far, it's working very well. I've been letting it run for a few days now. So far, it's working very well here. And oh, the error is that 0.006. Pretty good. It's just 100 images, but even with everything shifted and rotated, it's still outputting something good. So it still works. Anyway, we're just gonna do this here. Okay, get mean squared error. So let's start with the next one. Get sum. I'm just going to a list of functions that I found in TensorFlow and Keras. I'm just going through the function and see find the ones that could be useful, but it doesn't matter. I just picked them out. It doesn't really matter. Okay, sum. Now we calculate the sum of the. Oh, that's a dog barking. That's my dog. Okay. Okay, how do we calculate the sum? For I equals 0, I equal less than length. Sum equals 0, sum plus equals source. That's it. That's a simple one. Sum plus equals source dot I dot source. It calculates the sum of of all the items inside the array. That's pretty much easy. We don't need the register, and CUDA register 1 is equals sum, and we're done. There's no target. Get sum. That's the first one, and we're done. They're not going to be too difficult. Just well, some of them are going to be very difficult, but most of them should be easy enough. Result is a CUDA null unit. There's no target. We don't need that. Get sum. And source array length. Oh, let's copy that from here. We don't need to do it. We don't need to repeat anything. Okay. Sum. Yeah, we have the sum of all the items in the array. And easy enough, and then we're done. Oh, wait. We're not done. Okay, now we're done. Okay, next function. Just a list. Okay, next one. I have a list right here. Get the mean. I'm not sure why we need to know the mean of the array, but yeah, dog's barking. Get mean. Okay, length. Okay, same thing. Okay, now we need to compute the mean. Sum equals sum. Ah, still barking. Okay, dog always wants a treat. I can never have any peace. Okay, if length, more than one, sum equals sum divided by length, and we're done. Okay, that's the dog again. Okay, get the mean. This returns the mean value. Get mean. Okay, copy. Okay, that's 2 down. Next. Okay, I'm going to list. Get magnitude. Ooh, this one's slightly harder, but not by much. Okay, get the magnitude. That's the magnitude of the vector. If you want to calculate the distance, well, that's how you do it. The distance between two vectors, two outputs, or two arrays, and that's how you do it. Okay, get magnitude. How do we compute that? Copy the names. They're all exactly the same, so it doesn't matter. Okay, how do I calculate the magnitude? Okay, the magnitude is a squared plus b squared equals c squared, can be extended to any length. A squared plus b squared plus c squared plus d squared plus e, f, g, whatever. So you can extend it to any length, so it's just a matter of squaring it and then taking the square root. Source dot I. First you square it and then you take the square root. CUDA 1 equals square root sum. Oh. Thought it was going to be harder. It's actually very simple. Get the magnitude. Okay, if you want to calculate the length of a vector or the distance between two vectors, that's how you do it. Oh wait. Oh no, first you have to subtract. I thought you had to add two of them, but it doesn't matter. Get the magnitude. Okay, magnitude is done. Next, get the dot product. Ooh, not sure why I need. Well, actually, I'm not sure why I need any of these, but I still include them anyway. Get dot product. Product. Okay, source 1, source 2. Copy the name, just so we make sure you don't forget anything. Get dot product. Okay. The reason we are using just one kernel is because all the values are related to each other. So normally we use two kernels, multiple kernels, but since all the values are related, we cannot use parallelism when all the individual values in the arrays are connected to each other. So source 1 times source 2 dot product, source 1 times source 2. You just multiply each item in the array by the corresponding item in the second array. In the first array by the corresponding item in the second array. Okay. And then the sum is just the sum of the operation. That's it. Just add them up and that's it. Dot product. Now we have the dot product. Next. Yeah, these are easy. Easy enough. Okay. Next. What else? Going to the list again. Oh, here comes a hard one. Get the Euclidean distance. Actually, no, it's not. The Euclidean distance is exactly the same as magnitude. Like literally exactly the same as magnitude. I don't know why I put it on the list, but same thing. Get Euclidean distance. I need to remember how to spell Euclidean. 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 No. I'm trying to read it clearly just to make sure I can spell it right. Distance. That's exactly the same as getting the mean, except you have two values here: source 1, source 2. Euclidean distance, and Euclidean distance. Okay. Oh wait. Made a mistake again. Hahaha. Make a huge mistake. Oh. I just hope I didn't screw up any of the other places. Okay, source 1, source 2, source 1. So easy to make a mistake in these things. Okay, source 1, source 2, get magnitude source. Okay, Euclidean distance is okay, dot product is good. And just copy and paste. Uh, oh wait. Oh, I didn't change anything. Okay, source one, source two. Copy this. Okay, source one, source two. Oh wait, no, still messing up. I am still messing up. Source one, source two, and source two. Oh, we need to make sure that the length are the same, and we need this part right here. Okay, sum, we don't need that. Mean, we don't need that. Get mean, get magnitude, we don't need that. And now, source, get dot product, yes. Get magnitude, do we need it? Yeah, get dot product, we need it. We have to make sure that the two arrays are the same length. Source one and source two. So far, it's basic housekeeping stuff. Nothing really too difficult yet, but it will get a little bit difficult in the next one. I can smell it. Okay, source one, source two. Oh wait, copy that. Copy that. Okay, get Euclidean distance. So how does it work? Okay, we need to make sure you're getting it right. So equals source one minus source two squared. Plus equals source one minus source two squared. Okay, calculate the distance between the, it's the same thing, a squared plus b squared plus c squared plus d squared plus whatever else squared, and sum, and square with the sum. Okay, so far easy. It's just the distance between two vectors, which is the distance between 2 points. Each array has a point in hyperdimensional space, and you get the distance between them. That's easy enough. Okay, I probably made a mistake somewhere, but I will find it later. As long as you get the general idea, doesn't really matter. Okay, next. Okay, what's the next function? Oh, there's the big one. Cosine similarity. According to the explanation, the cosine similarity is the angle between two vectors. Okay, you treat each array as a vector, and then you find the angle between the two vectors. The smaller the angle, the more similar the two of them are, even if the angles are not the same length. It's not the same as the Euclidean distance. It's very much not the same, but it's the angle between them. Sometimes you need to know how similar two vectors are without measuring the distance between them. Cosine similarity. Okay, you have to know how this thing is used, but that's some really advanced stuff. I'm not really into that right now. Get cosine similarity. Get cosine similarity. All the parameters are the same, so we don't need to worry about anything else. Okay, cosine similarity between two vectors. Okay, this one's going to be slightly complicated. Okay. Oh, wait, there's no kernel. Because we have to do something a little bit janky here. Okay, source.init equals source.init. We don't need that. We don't need that. Okay, this is going to be complicated. I need to figure this out. I'm going to be reading the documentation to figure this one out. Just a minute. Okay, here's what I got for cosine similarity. And it's a doozy. Ooh. Okay. Not even sure I understand how it works here. So a dot b is equal to absolute value ab. Okay, the square root of the sum ab squared. Okay, that's the equation. And now we need to define exactly how this is going to work in code. Well, that's going to be a big one. I'm sure I can do it, but this is going to be a doozy. Okay, step one, what do we need? Okay, step one, there's the magnitude. That's the is it the magnitude or the absolute value? I'm reading this here. It's the dot product and magnitude as. Given the two vectors of attribute AB, the cosine similarity cosine AB is represented as a dot product and magnitude as. Oh, that's the square root of the sum squared. That's the magnitude. The magnitude, that's magnitude A times magnitude B times this dot product of AB. The product of AB divided by magnitude A divided by magnitude B. Wow, that's going to be a tough one. Okay, let me try and figure this out. Okay, I'm going to be reading from this and try to match it as well as I can. Okay, first we need the magnitude. Okay, CUDA neural unit. CUDA neural unit mag. Okay, what mag do we need? Okay, mag. Okay, if CUDA neural array get magnitude source 1. We need the magnitude of source 1 and mag. Okay, so this gets us the magnitude of source 1. What else do we need? Let me check again. Oh, we need a magnitude of source 2 also. We need two magnitudes, mag 1 and mag 2. Magnitude 1 and magnitude 2. Okay, copy this. Source 2. We got magnitude 2. Okay, what else? Okay, now we need to get the magnitude. And that's the dot product. Yeah, we need the dot product divided by magnitude 1 plus magnitude 2. Is it times magnitude 2? Let me read this. Yeah, it's times magnitude 2, not plus. Okay. Okay, let's copy this again. If CUDA neural get dot product. Get dot product source 1, source 2. Dot. We need dot. Okay, it may not be that difficult. Mag 1, mag 2, dot. Okay, we got the magnitude, the dot product. The magnitude of both of them plus the dot product of both of them. Now, what else do we need? Okay. Okay, let me just try and figure this out here. Shouldn't be too difficult. Okay, dot product, cosine similarity is sign. Now that's dot product equals magnitude A, magnitude B times cosine. So, so it's, I got this. It's dot product divided by mag 1 times mag 2. Oh, that's it. Oh, that's it. Okay. Let me just copy this here. My keyboard is supposed to be lighted up, but some symbols don't get lit up. I need to buy a new keyboard. Okay, result equals dot product divided by magnitude 1 times magnitude 2. Hey, that's it. Sum A squared, sum B squared, that's the magnitude. Square root of sum A squared, that must be squared, that's the magnitude. Magnitude 1 times magnitude 2, and dot product divided by magnitude 1 times magnitude 2 equals the cosine similarity. Hey, that was easy. Hey, not so hard. I thought it was going to be harder. Okay. Oh. That's pretty much it. Okay. Edit, advanced, format document. Okay, that's it. That's pretty much it. Like I said, I thought it was going to be harder. Okay, cosine similarity is done. Now in another function. Normalize. Okay, how do we normalize? Let's copy this. Oh no, let's copy this one. Oh, wait, nah. What am I doing? Okay, now we need to normalize. Okay, normalize. How do we normalize the function? A vector. Normalize. No. Normalize Z. Normalize. Ah, I can't type. Okay, normalize vector. Only one of them. Yeah. Reduce it to a length of 1. Oh, we don't need that. Don't need that. Don't need that. Do we need a result? Oh wait, no, no. Has to be done inside the. Oh, I'm gonna try to figure out normalize. This is so simple. I forget how to do it. Okay, I don't want to modify the existing vector, so there has to be a result. Result source. Wait, did I erase this? Oh, what am I doing here? Oh my god, why am I? Okay, I think I messed myself up here. Normalize. Why is it up here? Oh, normalize. Result. Results an array and source. Result array, source array. Okay, oh. Okay, result source. Okay, the names are confusing, but this two result array, source array. I don't want to modify the array, so best to copy it into a new one. Okay, result source is source, not result. Dot array length equals source dot array length. Everything's fine. Everything's the same. Okay, next, how do we normalize? Okay, step 1, we get the magnitude. Oh, convenient. Magnitude of source. Step 1, get the magnitude of source. CUDA neural array magnitude. Mag. Okay, step 1, get the magnitude. Step 2, get divide. Oh, we need to divide. We need to divide each unit by the magnitude. Oh, now we need a new function also. How to divide by a single value? CUDA neural array divide value. Okay, divide normally divides by one array by itself, but we need divide value. Divide by a specific value. Okay, result. Okay, I need to figure this out here. Okay, now we need to make another function. Result source mag. That's why I didn't get. Oi. Return 1. We need to create a function that divides each element in an array by a specific value. Okay, so we don't have it, so let's make it. Okay, while we at it, let's just make it one for all of them. Why are those here? Okay, fill one hot, add. We're just gonna copy all of them. Well, thought it was gonna be harder, but it's just tedious. Add value. Source value, and just change value 2 to a unit. It's tedious, but CUDA null unit. CUDA null unit value 2. And we copy everything. Value, not value 2 though, I did that, just value 2. Okay. Add value is for each item in the array, add a specific value as CUDA null unit. And easy enough, done. Okay, let's copy it. Let's make a subtract version while making sure we don't forget anything. kernel subtract value. Oh, yeah. Change that. Change that. Oh, yeah. And of course, I forgot something. CUDA null array field one hot. CUDA null array add value. Add value. I didn't. Oh my god. It's gonna be tedious. Value. This is gonna be really tedious. Just making sure I didn't forget anything here. I'm just gonna do this offline because otherwise it's just gonna take too long. This is just tedious changing stuff. There's nothing to learn here. Okay, back here. All I changed was I changed all the basic arithmetic functions: add, subtract, divide, multiply, to add a value function where you can add a specific value to each one. Okay, so first for normalize, you calculate the magnitude between source. Wait a minute, what do I call magnitude? Okay, you calculate the magnitude of source. How big the array is, and then you divide every value by that amount. Every value in amount, and you store the result inside result, one element wise. Mag is whoa, divide value. Oh, I made a few mistakes here. Don't correct that. Okay, the mistake was in divide value. Where is it? Where is it? Multiply value unit. CUDA null unit, not multiply. Okay, where's multiply? Multiply value. It's CUDA null unit, not CUDA null array. Oh, these are really small, stupid mistakes. CUDA null unit, CUDA, yeah. So everything should be, yeah, close to correct. Let me get back to where I was because that's just really stupid. Okay, mag. Okay, divide everything by the magnitude. Okay, compute the magnitude and divide each element by the magnitude to get the value, the total value, the total length of the array. Anyway, so it just reduces to normalize. It just reduces everything to 1. Get normalized, or should I call it normalized or get normalized? Yeah, get normalized, because we were returning a second array. That's just a more fitting name. Okay, so far easy enough. Okay, next, one more not so easy function, but hopefully not too difficult, is okay, get dot product. Okay, I have to pick one. Shuffle. Get shuffled. Get normalized. Get shuffled. Okay, get shuffled. Okay, shuffle is just randomize the value of each element of all the elements in the array. Okay, get shuffled is source result source. Okay, we shuffle it. Okay, result source, and there's no second result. Okay, source.array length, result.array length. Now result source. I just hope the names make sense. So it gets a shuffled version of the array. Every item is the same, but the positions get shuffled. Okay, keep forgetting to the names here. I need to figure out how I'm going to do this exactly. No, get dot product, get shuffled. Result source source.array length or result.array length. That's a matter of preference. There's no result. Return Why does that make sense? Oh, it doesn't. Okay, so there's nothing. There's no kernel calls in here. It didn't get normalized, but it didn't get shuffled. You need a kernel call. Okay, so how do you shuffle? You need I, J, and a temp value. CUDA null unit temp. A temp value. Okay, to shuffle something, you just go to each element. Oh, we need a random value. Cu rand. Okay, let me just copy from the random values here. Random, fill random. Okay, cu rand init. Maybe I'm going to need that. Cu rand init and state. Okay, it's going to be difficult to find out where I'm supposed to be here. Okay, cu rand init, and for I equal length, we get cu rand. Okay, temp equaled cu rand state. That returns a random number. Okay, now I need to know which one I'm going to be using. J. So I is the current position, J is a random position. Okay, so temp equals source, no, result. Oh, wait. Am I shuffling in place? Oh, this is going to be problematic here. That's going to be problematic. Because I'm shuffling in place. Now I need to figure out how to shuffle from one array to the next. It's not as easy as it sounds. Yoy. It's really not as easy as it sounds. Okay. Well, let's just do it in 2 steps. But why do it in 2 steps? Forget that. Just shuffle. I don't feel like figuring out how to do it. I know how to do it in place, but not doing it in the from one array to the next is a lot more complicated than it sounds. So let's just shuffling in place. Its result. Forget that. Okay, it's a lot harder than it sounds here. Just shuffle. Okay, result. Array data. We don't need source. Okay. Return CUDA memory synchronize. Okay, not shuffle, shuffle. Okay, just shuffle the every value. Zero and state. Now we don't need that. We don't need that. Okay, temp equals result dot I. Result dot I equals result dot J. Okay, result dot J equals temp. That just swaps the values of, you pick two indexes and then you swap the values in each one. Okay, and we're done. Oh, we need a seed. We need a seed to shuffle it. Random seed. Unsigned long seed. Yeah. A seed value. Okay, seed clock. Kernel array shuffle. Oh, we need a state. Just to end. Okay, cu rand state. Is that it? Oh, that's it. That's it. cu rand state. Okay. CUDA null init, cu rand state, and then we pick a value and then pick a value at random and then swap the locations. If it's the same one, then it makes no difference. We don't care. The clock. Okay, when shuffle, clock, and that's it. We're done. Okay, next. Okay, I need to pick these. Concatenate. Ooh. I either really like that one or really hate it. Okay, concatenate. Okay, do I need a kernel? Yeah, I need a kernel. I need a kernel. Okay, I need a kernel. Shuffle and concatenate. Keep two arrays and then combine them. CUDA null unit. Concatenate. Okay, we need a result. Ah, come on. No time for this. Result. Source 1, source 2. Yeah, just make sure that the names are the same. Concatenate. Concatenate. Result. No. Okay, we need a result here. Put that in front. Come on. Why won't it work correctly? Okay, take the value of take the values in two arrays and combine them into a single array. But first, we need to check out something. Nope. If source.array length not equals, now is result. Result.array needs to be equals to source.array length, source1.array length plus source2.array length. Okay, the size of the result array must be the size of the sum of the size of the source and of both the source arrays. The sum of the size of both of the source arrays. Concatenate. Oh, nah. This is getting really tedious. Get rid of that. Okay. Do I have everything right? All the sources are right. No, result. Result of array length. Okay, yeah, it's in the right place. Okay, so I do this here. Okay, wait a minute, is it? Oh, no, it's not. Oh, I need to do a little bit of magic here. Concatenate. Completely forgot that it didn't work the same way. Okay, 512 blocks per grid is result length x. Okay, I'm gonna do one kernel at a time, one pixel at a time. So because this one can be made independent just to make everything go faster. Oh, wait a minute. I'm just copying everything exactly, but it's not quite so obvious. Nothing's really different. Just have to make sure that everything matches up. Okay, source thread, source 1, source 2, result array length, blocks per grid. Everything is correct. Okay, everything's correct. Okay, there's no for loop. Oh, oh, I got it right here. Okay. No, this. No. Concatenate. Why do I need that? Could I know? No, I don't need that. Okay, concatenate. How do I concatenate? If I is less than value length, no, if I less than length, oh, if I, oh, there's a length. There's a length value. If I less than length, we result dot I equal value. Is it value length or source length? Oh, this is complicated. Oh, we need to know. We need to pass all three lengths, not just one of them. Oh yeah, yeah. Okay. Length 0, length 1, and length 2. Length 0, length 1, and length 2. Length 0 is the length of the result. If I is less than length, I'm reading this from something here. Okay, if I is it more than or equal? Oh, is it more than? It's more than or equals length 0. Return 0. If I is less than length 1, then result equal value 1 dot I. Not I. Oh shoot. Oh yeah, it's value 1 dot I. Okay. No, source 1, not value 1. Source 1. I'm thinking about something completely different here. Source 1 dot I. Okay. No, not return 0. You can't return a value in the kernel. Okay. Else result dot I equals value 2 dot I. No. I'm thinking about something else again. Source 1. Source 2 dot I. It's not exactly I. It's I minus length 1. Okay. So I need a length 2. I don't need it, but I still use it. Okay. If we are within the range of the first one, then we take the I value. If we are not in the range of the first one, then we take the value of the second ones minus the length of the first one. Okay, that's concatenation. There's something else I need to do, but yeah, I can do that quick. Concatenate, and another one that's very important, it's split. They're basically the same thing. Split. All the names are the same thing. Split. It does exactly the same thing, but in reverse. It takes the value in the result and distribute them between the source 1 and source 2. Split. Oh, that's easy enough. It just takes a while. I would have thought this one was going to be. I thought the get cosine similarity was going to be the hard one, but this one turns out to be the hard one. Okay, so we just reverse everything here. Source 1 dot I equal result dot I. Source 2 dot I minus length equals result dot I. Yeah, this one turned out to be the hard one. Okay, that's pretty much it. And we're done. If there's any errors, I'll correct them later, but so far everything is good. I'm just gonna clean this up, but I'll do that offline. But so far, we're good here. That's enough for tonight. Time to go to sleep. Okay.